So what we had before was it's like a topological space that locally looks like R to the D. So like you could chart it onto some R like Cartesian axis. But formally, that results from the fact that it is a paracompact Hausdorff topological space. And that's only if for every point. Okay, wait, so it's actually both. So one, it has to be paracompact and Hausdorff, and two, for every point, like there's an open neighborhood, and that open neighborhood, it's homomorphic to like R to the D. So you can chart that open neighborhood on R to the D.
Or even a subset of RD.
Yeah, a subset of RD, right. It doesn't have to be the whole thing. And so breaking down that, I believe, so Hausdorff was like,
oh wait, I have
for any
a
2
question.
points you can.
Is it so homeomorphic to RD? Do you mean like homeomorphic to RD equipped with the standard topology? Because homeomorphic is the isomorphism for topologies.
Oh wait, so it says, so there's a homeomorphism, so there's a map from this to that, and yeah, it's RD with the standard topology. So that's
because it's a homomorphism. They didn't say like just bijection.
Yeah, and you always assume standard topology when they do that. Hausdorff, I believe it was like if you have two open, like we shouldn't say open balls, but like if you have 2 points and then you get an open subset that contain those points, then those things don't overlap. I believe that's what it was. And
measure of coarseness or of fineness.
Yeah, and paracompactness. Well, looking back, I think it was like harder for me to define because it was like every open. It was something about open covers and refinement. So that's kind of something I don't quite remember.
It was every open cover it is locally finite. Wait.
It was something like I guess I could like look it up, but
it has a locally finite subcover or locally finite refinement. I believe.
Yeah.
Refinement.
Wait, actually, let me just check.
Oh no, locally finite. Yeah.
Okay, I have it somewhere here, but like I don't know if we should talk about it or not.
Yeah, it's not that important.
Yeah, like intuitively, it's just like you can chart it on some R to the D, like chart a local section of it. So, and when you say chart, that means like you can take like a certain region of it, and then there's a map that you can use to like transfer each point from that real world to your Cartesian axis, sort of. Yeah.
Do you know why it has to be Hausdorff, a topological map? I mean, I think the truth is it doesn't actually have to be Hausdorff, but it is a practical condition to enforce.
I feel like making it Hausdorff is one of the things that lets it be possible for it to chart onto the real line, right? Because if you have, I mean, that's how I imagine, because on like in the real, in like R to the D, if you take any 2 points, there's like an uncountable number of points between those 2 points. Like no matter what.
Which is a powder though, that's just always going to be true.
Yes, but RD with the standard topology. So it's like the coarseness has to be the same, is what I'm thinking.
Between the two.
Like the coarseness of your.
How about this? Let's pretend we have a topological manifold. So some powder equipped with, let's say, the discrete topology. Or which one is
a manifold? I don't know, because like a manifold is defined such that it like satisfies those conditions, right? Like the conditions that it's Hausdorff and paracompact.
No. But I'm saying in the previous video, the definition didn't include Hausdorff and paracompact. So I'm saying it's a choice. But from I think I've done some thinking here, and it seems to be a practical choice. I guess here I might as well explain. Yeah.
Mm-hmm.
Okay. So the intuition I have is that Hausdorff is a measurement of coarseness / fineness. If a topology is discrete, I'm sorry, it's the opposite. If a topology is chaotic, so if the topology is only like the M and empty set, then think about this: a map is continuous if the open sets or the pre-image of open sets are open, right? So if the guy on the receiving end, right, the pre-image of open sets are open, the guy on the receiving end for the pre-image, if his topology is the discrete topology, then the map is either always going to be continuous or never continuous, right? If this guy's topology is discrete or chaotic. So I think the reason why it's adding the fact that the M's topology must be Hausdorff is because the next condition talks about a homeomorphism between neighborhoods of M. And if M was equipped with the discrete topology, for example, then the homeomorphism is always going to be there, you know, like every single map is homeomorphic because the open set of whatever is here, like it's always going to be open because every single thing is open and they were seen. So I think it's just a practical condition to limit like dumb manifolds. Because, you know, I could give some random shit, equip it with the discrete topology, and boom, now it's a manifold, unless you specify that it's Hausdorff.
Oh, interesting. Because I thought it was because, so if you want to like, I don't know, like if you draw a donut and you want to like chart it onto chart like a part of it onto like a Cartesian R to the D axis, right? You want there to be the same level of coarseness such that your surface of your topology, there has to be 2 points with like those balls around it that don't overlap. Like that, like there have to be those 2 balls have to exist. Because if they don't, then it would be weird to define a map. Because in R to the D, it does exist, right? Like you've got 2 balls. Like for any 2 points, you can draw balls around them that don't overlap. If you can't do that for your original topology, then how are you gonna? I'm like, how could you make a continuous map like that? Like, that's what I thought.
See. But pause. Let's agree with this. So a donut, like the idea of a donut in set theory without any additional structure is just a powder, right?
Yes, but with topologies.
If I equip a donut with the chaotic topology, then the donut is not a.
It's not a donut, really, as we know.
It's not a manifold anymore.
Yeah, but you can't really call it a donut anymore because, like, then it's just like a bunch of points, right?
Yes, exactly. But if I equip it with the discrete topology, then it is a manifold.
Is it?
I think so. Think about it. Any subset or any open neighborhood of the donut has a homeomorphism to RD. What's a homeomorphism? Bijection plus continuity. What's continuity? The open sets of the subset of RD are going to be open in M or in the donut, but the donut, every single set or subset is open, right?
That makes sense because if we're starting with a donut and we're saying remove its topology, and so we're just talking about its set, then that set is uncountably infinite.
Yes.
Because if we start with a donut, right? Like, yeah, it's an uncountably infinite set. Like, can we agree on that?
Sure.
So I mean, to me, it makes sense. Like if you take an uncountably infinite set and then equip it with like, was it chaotic or discrete? Like the one where it has like all.
So chaotic is the one where it's like just the empty set in M. Discrete is like everything.
So if you take that, so if you equip like that uncountably infinite set with a discrete topology, then to me that sounds like it has to be a manifold. Yeah,
like anything you equip with the discrete topology will be a manifold.
Except, I never thought about that, but that kind of
because everything's just a powder, right?
Would it though? Because like I can take the set 1, 2.
It could be the discrete topology. Now it's a manifold.
Is it a manifold?
Well, depends on the definition you use of a manifold. If you use a manifold as just being a topological space with local homeomorphisms to RD.
Oh yeah, because like 1, 2, like if you equip with discrete topology, it's not Hausdorff. So with that definition.
Yeah, exactly.
So that's kind of why we need that definition. Okay, that's interesting.
It's blocking out the dumb ones,
It's blocking out stuff like that. Yeah, okay.
I wonder if paracompactness does the same thing, but in the opposite direction.
The thing with paracompactness, I don't think I fully grasped it.
Yeah.
But I do remember it was like a very natural thing. So it's like.
Yeah, it's going to happen all the time.
So I feel like if it wasn't paracompact, it just wouldn't be natural to make it to chart it onto the real world or onto the real.
Okay.
Cartesian,
yeah, I don't know. We'd have to do more thought thinking
into that. Yeah.
Here, let's go to the next one.
Yeah.
Manifold dimensions. Oh, here, do you want to? Oh, I think we've already done this in the past. I was about to give examples of topological manifolds, but let's move on because we've already done that in the past.
Wait, hold on. I'm just like skimming through the notes right now. Yeah. Okay. Yeah, I guess we can move on past dimension.
So yeah, manifold dimension. That's just the dimension of the subset of RD that the homeomorphisms will locally map to. Submanifold. I think we use submanifolds like every single time that we do interesting things.
Yeah, submanifold is like, so you'd start with one manifold and then you take, so, I mean, I don't know, should we just like open the writing thing?
Oh yeah, here.
Although this isn't really necessary in this case though. Yeah, it's pretty simple because like you start with one manifold,
yeah,
and then you take another set and then you inherit the topology on your original manifold. Like, and if this new thing is a manifold, then it's a submanifold.
Exactly. Like if we have the R2 standard topology, the one we always use, and then we sculpt out the circle.
Yeah.
And then the subset topology here, then this is just as a manifold because this one happens to be manifold. Yeah. By the way, I saw a YouTube comment mentioning that this is an inaccurate definition of the submanifolds.
Oh, really?
So just a food for thought, but not that we're going to use like submanifolds that much. Like we've already been doing this. Now we just.
Yeah, I kind of feel like if it's wrong, it can't be that wrong that it's going to screw us over.
Yeah, exactly. Because yeah, I don't feel they're used that often. If Schuler would have made.
I do want to point out like this interesting thing that he brought up in the video.
Okay.
I think it was like this. So you got like a circle. Wait, I'm not writing. Whoops. Actually, wait, I can just do this. Yeah, circle. Ooh. And then another circle like that. And let's say they intersect at like one point.
Oh, yeah, so sure.
This is...
No, but open sets aren't circles. They don't have a hard border.
Open sets... No, so let me say like this thing is like a manifold.
Oh,
or like a topology.
You're sculpting it out of R2.
Yeah, so like the thing is like, I remember he said like, this is not a submanifold of R2 with standard topology because of this intersection point.
Well, it's just not a topological space, is it? Oh, yeah, you're right. It is a topological space. It's not a manifold.
Yeah.
Oh.
But yeah.
Okay.
Because wait, hold on. Let me remember why. Because it was like, yeah, because you can't. If you were to chart it onto the real line, like if you took an open interval, I don't know, like there's this bifurcation here where you can go in both directions. So that kind of like messes
it's just a test, right? First you test, is it a 1D manifold?
It's not because of this.
Yes, right? Then you test, is it a 2D, and then you like.
It's not 2D manifold because.
Like I think this point would be 2D. Oh, no, it's just.
No. Yeah, because I don't think you can like chart this space like onto a 2D thing. Because you're just like charting all of these points. I don't know.
Okay.
Actually, I'm not really sure.
Anyways, yeah, let's go to the next point. Product manifolds. That one's kind of important, but also kind of obvious, I feel.
Yeah. I don't know. Do you want to take it real quick?
Sure. So product manifolds, we already know how to take the product of sets. That one's not an issue. You just tuple them up. So then the question becomes, what do you do with the topology? And the rule is straightforward enough. Like if you look at it, it is just intuitively, it does what you expect it to do.
What does it expect to do? Maybe you want to give an example?
Sure. Cylinder in R is usually a good one.
Mm.
I don't have it with me though.
Or actually, I see like on the notes, it's like cylinder is equal to S1 cross R.
Yeah. So this isn't an issue on sets theory wise, but the question is what happens on the topological level?
Mm-hmm.
Let me check what happens on the topological level.
Oh, I think I get it, right? Because like you have like a circle. I think you actually talked about this in the last time, right? Like you have a circle and then you get like a real line and then you get
but that's the subset topology. Oh, wait, what?
Yeah, so I guess we're assuming like, oops, what happened?
go ahead.
Yeah, okay, so you start with a circle, and I guess we can assume like it has the topology, like it inherits from the standard topology, right? So yeah, and then so if we're saying a cylinder is equal to this is awkward. Wait, hold on. Oh, yeah, cylinder is equal to circle cross real number line, right? So you've got your circle here, and then at every point you kind of get like a line, right? So then that ends up becoming a cylinder.
Mm-hmm. I mean,
Except,
since it already goes both ways.
But... Yeah, and it goes both ways, so it's like infinite, like an infinite cylinder.
Yeah.
And then the two torus, right? It's like, which is just the torus we're used to. I believe it's just this cross this because. So you
Yeah.
take a circle, and then at every point
circle,
you've got
circle and a circle. Okay, cool. Okay, so that leaves us for the next thing, which is bundles. Okay,
we blazed through that really quickly. Now this is the real stuff.
Do you feel comfortable explaining bundles?
I think you should start.
Okay, here. So let's see. So taking, okay, first of all, I need to be very clear on one thing. Products can be used.
Hey, David, very quick question.
Yeah.
Is cross distinct? Is the X symbol a cross product, or is that a very different thing?
Yeah, it's a cross product. Yeah, whenever you go S1 cross R. The issue here is that as a set, this is the Cartesian product, but the question is what happens on the topological level. So what happens to this guy?
Is a cross product and a Cartesian product the same thing?
Yeah, yeah.
Wait, what?
Wait, no. Sorry, a cross product from linear algebra. No, not at all. Completely different.
Okay, just checking. Okay, keep going.
Yeah,
we've been saying cross instead of times or.
X. Yeah, we should say like Cartesian product.
My bad. Yeah, this is Cartesian, not cross.
Yeah, because we just see an X and we're like cross, so it's like Cartesian.
Big mistake. Yeah. Okay, here, let's go. So I need to be very clear about something to explain bundles, which is that we can understand things. So if I have this multiplication sign, right, I can use it for two purposes. Number one, I can use it to create new things from old ones. I can go 3 cross 4, 3 times 4, and say this is 12. Okay, that's not an issue. But what I can also do is I can take 12 and I can understand 12 as being made up of components 3 times 4.
Ooh, yes. And this is kind of what we do with prime factorization. We just break a number down into primes.
Yeah. So the multiplication sign has two uses. It can be used to create new things, or if you already have the 12, you can use it to, analyze 12 as, being a part of its, like, as having components. So the same exact thing happens with the product between manifolds, which is that, yes, we can create new manifolds from old ones, like going S1 product R. But when we're talking about bundles, creating new manifolds isn't our goal. Okay, that's not where bundles come in. Bundles only are useful if you're trying to analyze a space that already exists and to understand it as having components, decomposing this total space into its components. The reason is because the definition of a bundle is a triple, E, pi, B. Total space, projection map, base space. Now, how weird is it for the definition of a bundle to include the total space? Okay, it's actually normal if you're trying to analyze this space, but this just clearly shows, okay, if your goal was to create new spaces with bundles, then there's no way that you would require the total space as a part of the definition for the bundle, right? The bundle is only a tool for analyzing manifolds you already have, right? Like if I give you the Möbius strip, I can create the Möbius strip just fine without products, without bundles, using this, like the quotient, right? Like the quotient space. I can like say glue this to this, but with a twist, right? You can do that just fine without bundles. But what bundles are used for is to take something like the Möbius strip, say, okay, E is going to be like set theoretically the powder that is the Möbius strip plus the topology. And I can decompose the Möbius strip as having a projection map and a base space. In this case, the base case is a circle. Same thing with the cylinder. So I have a cylinder. I can create the cylinder just fine without the product, or I don't know, like, you know, you could do the same thing with quotient space and glue, but without a twist. You could also do it with products. That's not an issue. But the point is that you need to already have the total space defined if you're trying to, you know, use a bundle. Okay, kind of dumb.
Now that's interesting. I didn't think of it like that, but yeah, you're right. You need to have a total space first because bundles are just a way to decompose it so that you can understand them.
Exactly. Understanding it as having components. And usually I guess that makes life really easy for things. But here, take a look at this. So I gave my example of 12 is equal to 3 times 4. Now I'm going to give a dumb example. Dumb because this is like dumb, but for like understanding the reason of a bundle, it's actually pretty cool. So a bundle is kind of like if I was writing 12 as being this, a triplet 12 divide by 3, 4, parentheses with fibre 3, if you can see that, if you can see why. So I already have 12. That's not an issue. I already have 12, but I'm going to understand 12 as having a projection onto 4, and then implicitly having a fibre 3 because, you know, 3 times 4. But the reason that this example is dumb is because it doesn't acknowledge the fact that with manifolds, you can have like hidden twists that would be like just fine here. In this case, numbers obviously don't have any twists. So this is completely trivial. The word is trivial, right? Like why are you doing this? It's trivial. But for manifolds, it's not trivial. Unless you choose to like decompose the cylinder using this triplet, when you really just could decompose the cylinder as 12 is equal to, you know, 3 times 4. So that is the purpose of a manifold. It's not to create new spaces.
It's to understand
spaces that already exist. Exactly. So now we can give like a bunch of examples. Let's see, we're gonna have total space E pi B. So okay, I'm gonna say beforehand intuitively that my example is going to be the cylinder with the base space of a circle. If I wanted to use the structure, like this is a lot like a class, you know, like the idea of a bundle is kind of like a class where you can have methods defined for that class.
And the pi is the method, or no, that's not true.
So basically I have things that I write down, methods for general bundles, like formulas that I can use for general bundles. It applies to every single bundles.
Okay.
And then I can use these techniques, since I know that they apply to every single bundle. I can use these techniques to any instantiation, right? If I give an actual example of a bundle, like cylinder, whatever, map, circle, I can use these methods. Like, you know, I kind of get them because
it's just like that's just how bundles work.
Yeah.
Like it's just the logic of bundles, kind of like how they work.
Yes.
In general.
So, okay, anyways, I'm going to walk forward intuitively. The example I'm going to give is cylinder projection down into circle. But if I actually want to use this framework, I need to have a manifold here and a manifold here, and I need to show that they're manifolds, and then I need to have a map down. Starting off with the base space. So intuitively in my head, I just want a circle. I'm going to say, okay, start with R2 with the standard topology. So now I have this big sheet. I'm going to sculpt out S1 with the subset topology. Okay, now I actually, technically, I would have to prove that this is, first of all, a topological space, and second of all, a topological manifold. You have to prove that. No issue. In this case, you believe me, or
yeah, I think we've done before, right? Like when we had like we had a circle, you do this open ball thing, and then now you've got like this open interval.
Yes.
So then bam, right? So that's basically the
topology.
idea.
Yeah, and to prove that it's actually a manifold, you'd have to give the proof that whatever, it's Hausdorff, that it's pair compact, that first of all it's a topological space, right? So the topology includes empty set M, whatever, all that stuff. And then you'd also have to prove any open neighborhood can map down it. In this case, you just believe me, right?
Yeah.
So now we have this check mark. We successfully formed it. I'm going to call it S1, but really it's S1 equipped with the subset topology.
Yeah.
So now we formed that element. Next, I'm going to form the total space. So again, I'm analyzing a cylinder. What am I going to do? In my head, I'm going to use S1, right? Because cylinder, I can kind of cheat. So we have S1 here. Next thing I need to define is R, equipped with the standard topology. And I'm going to take the cross, the product between these two, S1 subset topology. And this is going to give me cylinder, C. We'll say, I don't know, C1, whatever, equipped with, the product topology. So I'm using the product here to create E. I'm not using it like as a bundle. This is like a prerequisite to using the structure that is a bundle. Okay, so now I have those two. I have B, I have E. I actually need to define pi. How am I going to define pi? Let's see. I'm going to say pi is a map that goes, okay, obviously from E to B. That one's not an issue in terms of like the types here. But in terms of what's actually happening on the ground, we're going to say it's going to take so cylinder is going to have, let's see, I made the product between S1 and R. So a cylinder is going to be a tuple. S1 is just based off R2. So it's going to be a 3-digit tuple. It's going to be XYZ. This is my cylinder. My total space is going to take an XYZ. Intuitively, this is just the coordinates of the cylinder, right? What's it going to do to that XYZ? This is pi I'm defining here. What's it going to do? It's going to X, Y.
Shouldn't it only take it to one factor? Like
Yeah.
one of like either just the circle or just the real line. And in this case, it would be the circle because
in this case, we
circles are
want
base
B.
space.
Well, yeah, we want B, which is S1, which is going to be a tuple with 2 entries. So in this case, it's just going to do XY. And this is pi.
Yeah.
I'm done. Now I have defined a bundle, and all of the nice associated methods that come with a bundle, I can use them on my example here and understand the cylinder as having components.
Intuitively, that would be like if you had a cylinder like this, right? Infinite, of course. And then like, let's say you like took a point here, like your map pi would bring it down to this.
Yes.
Like, let's say this specific circle.
In this case, I would say actually maybe a vertical cylinder might be more accurate because I'm getting rid of the Z coordinate, but in essence, yes.
Yeah.
Okay,
Cool.
sounds good. Next, I'm going to give an example of a Möbius strip, which, so yeah, that's intuitively what's going to happen. In practice, I actually need to define each of these. So Möbius strip, the base space is just going to be S1 again, no problem. Total space, this is a bit more complicated. I'm going to take R2, equip with standard topology. Now I'm going to use the quotient topology to glue them together, but with a twist. Oh, no. Wait, that's wrong. I'm going to take R2. I'm going to sculpt out a little sheet of paper, like the one that you have over there. Yes, I'm going to sculpt this out and equip it with the subset topology.
So we've got this strip. Yeah.
Yes. Next, I'm going to quotient topology the ends, but with a twist.
So, okay, wait, hold on. So you would glue it, but then you twist.
Yes.
Actually, I don't know if this is close enough to it. So normally you would glue it like this, but now we're gonna twist it so it's like that.
So just to be very clear here, I happened to sculpt out a piece of paper around. So remember, this is the point 0, 0.
Mm-hmm.
But R2 is a powder, okay? That doesn't mean anything,
Yeah.
okay? Like this is just a random point that I happen to pick. And so now this one happens to be, right beside that one because of the
We're just defining it this way.
Yes, that's how we choose to define it, which means that like our total space here is just going to be a powder, like it's going to be a tuple with 2 entries, which represents this piece of paper, but with the idea that there's a twist in it, right? Equipped with the quotient topology, which somehow gets defined. I don't think it actually matters how. The point is that intuitively, like whatever open sets, like you're going to be allowed to have an open set like this, I think, is what's going to happen practically. That's kind of cool though. Look at this. It's like an open set that's half here, half there. But what's really happening is that you're copy pasting these pieces of paper like this, but with a twist, you know? Like this.
Yeah.
So I don't know, kind of cool. Oh wait, I have a little bit of an issue here, because never mind.
Okay.
I think my issue is that, look at your piece of paper, like show me your piece of paper, like just show it without the twist, just the sheet of paper. Okay, good. So now we have this. What about the back of the paper? We never talked about it.
Yeah, so that's an interesting thing. Like I didn't draw a line on the back intentionally. I feel like, yeah, that's something that's kind of confusing, because if you do, like the thing is, like once you do the twist, you end up with, like if you draw the line beforehand and then you do the twist, you end up with like this weird transition, right? So like where the line stops.
That's a problem.
But I would imagine like,
I'm sure it's solved somehow.
but the line, but by gluing it together, like this is what I think the solution is, right? By gluing it together, you're saying that the line is supposed to continue.
I don't know. This still feels like an issue.
I mean, right? Because like,
where are the points coming from? Where is the powder coming from?
Oh. The thing is, the weird thing is because it's like this paper is 2D. So like there is no back.
Oh.
That's the weird. That's what makes this thing kind of weird. Like this is like,
if you took your paper there and you kept on, getting it closer and closer and closer.
Yeah. So like eventually, like
the
pencil, like if this was 2D, then the pencil-led atoms, like there would be, like if I drew something on one side, it would be on the other side because it's just one atom of pencil lead. Yeah.
Cool.
So that's why that happens.
Okay, interesting.
That's kind of cool, actually. Yeah, because it's 2D, so there is like the front and the back are the same point.
Yeah, our imagination and intuition is coming to throw us off, but
yeah, we saved it.
In any case, so yeah, we have the E here successfully defined now. We have the B successfully defined. Now the question is, how the hell is pi defined? So pi is always going to go from E to B. That one's never going to change. But in terms of practical implementation, E is just a tuple with two entries this time. So it's going to take an X and a Y. What is it going to do to X, Y?
So B is a circle, right?
Yeah. I think what you need to do is you need to like implicitly say, when I took my sheet of paper, this was 0, 0, right?
Yeah.
The point in the middle here. And this here is like 1, 0.
Oh, I think I sort of get it. It's like if I, hold on, I don't know if I should put this up to the camera, but like you see how there's there's kind of like a circle, like a dark line in the middle. That's kind of like a circle.
Yeah.
So we can say that any point on the Möbius strip, we project it down to the nearest point on the circle.
But what is the circle? Like I need to tell you what 0 is pretty much.
Yeah.
I think that's fine though. Like you just are very clear. Like this is a powder, right? E is a powder, which means in theory, I should be able to look at that powder and make a choice of like, I want this to project down into, let's see, it glues the X. We want the Y to always be 0. So this would be X0 essentially.
Yeah, you could do that. Another interesting thing is that like before they got into bundles, like what they talked about is like having the Möbius strip locally looking like this, right? S1 cross the closed interval 0 to 1.
Yeah. Locally, yeah. Intuitively, I agree.
Yeah, but then again, like globally, that doesn't work, and that's why you gotta have it like a different kind of bundle. Is that how it works?
What do you mean?
Actually, no.
Because this definitely is.
Is this valid?
Möbius strip.
Huh?
100% what you wrote down is a cylinder. It's not a Möbius strip though.
This? Yeah.
100% not a Möbius. It doesn't have the twist.
Right. Yeah. Never mind.
Yeah. Like if
but
this is
locally it looks like that, but then like you can't make it globally. Right. Never mind. I get it. Yeah.
So you actually have to like define the Möbius strip E. Like you have to go to E using like the quotient rather than the other dude, rather
Yeah.
than just the product. So that goes to show that the product isn't really related to the bundle that much.
Product isn't really related. Yeah.
In terms of motivation, I can see why, but practically, I don't know.
I mean, like, especially like if your if your bundle is like that kind of one where it's just like a product topology, then would you say that it is?
Oh,
Because
then
like you
it's
take one
related.
factor.
But in this case, with the quotient, I'm just saying, oh, the bundle is really just an extended version of the quotient topology, of the quotient, whatever.
Yeah.
I don't know.
Yeah, I guess.
It's more like the quotient and the product are used to create new spaces. So the bundle, in a sense, is their reverse. It's their inverse, because a bundle takes a space that already exists and analyzes it as having, components.
Mm-hmm.
So
Wait, one thing that's kind of interesting, like in this like paper that you've drawn, are these like, this is like a closed paper. So then we have like a -1, like -1 0 point here, and then a 1 0 point here.
Sure.
When you glue them together, like then this point.
Oh, is both?
Is big. Yeah, it's like it's both.
We'd have to look into how the quotient space works, because intuitively I can say, okay, I just glue them together, but mathematically what actually arrives, okay, you're probably gonna have to be like, do some research.
Yeah, it's just like 1 is equal to -1.
Yeah, I don't know.
Which I don't think is wrong, actually.
Yeah, it's fine. You're just creating a system where that's true. Like,
yeah, you can do that totally.
yeah, mathematicians.
Yeah.
Anyways, okay, let's see what's next. Fibres.
Yeah. Let me see. Do I understand fibers well enough to explain them? I don't know. I know like. Okay, so let me just like have the definition. Let me just like write the definition up and see if I can.
Okay, sure.
Like if I really understand. So I've got this e pi base space, and that's a bundle, and we've got a point P that is in the base space. So the fiber attached to that point P is the pre-image of the pre-image under pi. So the pre-image of the set containing the point P under pi. And intuitively, aha. Yeah, okay, I think I get it. So like there's a picture in the notes, right? Like it's just like it's like a little manifold here. We'll call this M, or we'll call this B the base space, right? And then you attach like let me do a different color. So we'll attach like a fiber. So imagine this is a line in the third dimension, right? And it's just going through here. It touches this point, and then yeah. So like imagine I have a flat plane and I've got like that, right? Like this red thing is the fiber, and then here is the point P, right? So what the map?
And where's the total space?
So let's say that the total space is like the union of this with like fibers attached to every point. I mean, I don't know if you can. I don't know if that's general enough though.
No. Basically, you're saying it's a product between the fiber and the base space.
Yeah, I guess. Yeah.
But why not just say the total space is just 3D space?
Sure. Yeah. I mean, I guess so. And then honestly, like, yeah, okay. Let's say the total space is 3D space, and let's say that each of these fibers is like a straight line. Like, yeah, it's like R, and of course, standard topology, all that stuff. What we could say is like, let's say we have this bundle such that pi basically takes any point along 3D space and projects it down onto this 2D manifold, right? Yeah, so it's like you just remove the z-axis. Pretty simple. And then we say that the fiber is the pre-image of pi. that means, so basically what this manifold is doing, so what this bundle is doing, we've got this manifold in 3D space. We've got a 3D space, that's our total space. And our base space is this flat line and this flat plane. And let's say like right here is the point P and there's like a fiber attached to that point P. What we're saying that we have defined pi such that it takes every point along this line and just like squishes it down onto this manifold. So the pre-image is like, if you undo that, not undo, because it's not like an inverse map. It's just like the domain is this entire line. Like for this point, the domain of the map is the entire line.
Yeah.
And like
the pre-image.
And the image is just that one point P. So yeah, that's what pre-image is. It's basically like the set of, so like the pre-image or like the fiber for a particular point is basically the set of all the points in the total space that collapse down into P.
Yeah.
That become P when you go from total space to base space with pi.
So yeah, the pre-image of the map pi at the point P, essentially.
Yeah. So it's actually kind of intuitive in that sense. Or not kind of, I think it's pretty intuitive. Yeah.
It makes sense to me, yeah. I mean, do you want to talk about fiber bundles now and if they have to be unique and not unique and weird bundles?
How about you go ahead with that?
Sure, I got you. All right, let's see.
Should I clear this? Oh, you can.
Yeah, I want to cover it. Okay, so so now we know what fibers are, right? We have like our space. Every single one has a fiber. And then this is the total space, the base space, the map pi that goes down.
When you say total space, you mean like everything, or like?
Yeah. I mean, like in this case, the total space would just be R2, like intuitively.
Mm-hmm. But you can think of it as actually, in this example, you can kind of think of it as the union of this line with all these fibers.
Yes, but that's not the idea behind a bundle. The idea behind a bundle is you come in already having the total space.
Yeah.
You come in already having the base space and already have it. And then you do further analysis. So, to avoid circular logic in this case, I'm going to put that I've
because like what I just described, it's like, that's a classic example of like a product topology. But in reality, we want to be more general than that.
Exactly. I don't want my bundle to just be a product. I mean, that's okay sometimes, but to understand what a bundle is, it's more general. So yeah, the idea, again, like a bundle, you already come in with an E, you already come in with a B, and the F is implied, which means that you can come up with normal bundles, like bundles that I'm going to say are trivial because they like intuitively make sense, like you're talking
because
about.
They're like product
match
topologies.
this.
Because they're product bundles.
Yes, exactly. And what the definition of a fiber bundle is where every single fiber is the same. Okay. Is it really the same though? So the reason is that we write down a fiber as FP because the fiber is going to be like a tuple. In this case, it's going to be a tuple, right? If we pretend that E is, R2 or something. So in this case, we're going to say this fiber is, it's going to be a set with a ton of tuples, right? Mm-hmm. Which means that the tuple here is going to be different from the tuple here. So the fibers are never, like as a powder, the fibers are always going to be different, right? As a powder, the symbols here are different than the symbols here, different than the symbols here. But what we say is that if every single fiber is isomorphic to each other.
Topologically? Or
is it
set theoretically?
Interesting. Is it?
I feel like it would be topologically, but I can't be sure. Or is it like?
It's a good question. Let's see. Let's refer to the definition. Yeah, topologically isomorphic. That's so weird. How the hell do you get a?
Because the fiber itself is a topology, right?
Yes. I guess that must be the case then. I mean, intuitively, sure, I agree with you, but like, I agree with that statement. It means that you need to equip. Like, whenever you do your operation, you say F is defined as pre-image under pi of the point P. You have to somehow equip F with a topology. Can you do that?
Mm-hmm. Wait a second. Did we mention that pi has to be continuous and surjective?
Oh, okay. Well, that's new. I mean, shit.
Okay. Well, that's the thing. Yeah. So
clarify things.
So I mean, pi is continuous. That sort of intuitively makes sense. Preimage of open sets in the base space have to be open in the total space. I feel like, right? Like if you, like honestly, if you go down to a point like its pre-image should be open.
Yeah, like F is going to be a subset of the total space.
And then surjective.
Wait,
surjective,
does that mean? Because if F is a subset of the total space, you can just equip F with the subset topology.
You could. I
But
guess
isn't the
so.
right way? Maybe there's another way. Anyways, but surjective is.
I believe it was like every set in the target, every point in the target gets hit.
Yeah.
So yeah, so that makes sense. So like your base, like if you have a base space, every point on that base space like has to be hit by this map. So like if you go from the total space, your map pi takes you from the total space to the base space.
Yeah.
Like that base space has to be included in the total space completely.
Exactly.
So yeah.
It's like if I took a circle as the base space, the product of the circle in R as the total space.
And then you like left one point out.
Or even if I came back to the definition of my base space and added a little line here or something.
Yeah.
Yeah.
Or it would be like, if you have like, I feel like leave one little point out, then it's like, it's not, it's like pi, like you need pi to hit this point somewhere. Otherwise it's like not even, it's like not a valid pi.
True. Okay, so that's, so anyways, the point is a fiber bundle is whenever all of these lines are isomorphic, right? It's not that they're equal. They can't be equal. Each of them are separate powders with different tuples, but you can create, like have an isomorphism between all of them. And if all those isomorphisms are the same, then you have a fiber bundle. Which means now we can do this really nice thing. We can say bundles are the far west or whatever, the crazy land. Then you have fiber bundles, which is less crazy. Product manifolds. Okay, here you go. I finally, this is beautiful. This should be screenshotted and put onto a shirt. So bundles is like the Wild West because it has no restrictions. So you can give the weird freaking examples. We have a circle that gets smaller.
Yeah, it's crazy.
Point, and then a line, fiber completely different everywhere.
Their only restrictions really are like, I mean,
well, pi has
to be continuous surjective.
That's literally it. That's insane. Okay.
Yeah.
So anyways, that's a bundle.
I mean, that's not trivial. That's like, that does like, I mean, that's not like everything, but it's like compared to fiber bundles, that's everything.
Yes. So yeah, then huge. Fiber bundles is like less crazy, and then product manifolds is like baby land. So
yeah, so fiber bundle, again, basically each fiber is topologically isomorphic to each other.
Exactly. So something like this would not work out.
But the interesting thing is like if you have this line, right? Oop, what did I do? Oh God. So if I've got a line and then I have like a long line, like I call this my fiber, then if I have a shorter one, these two lines are topologically isomorphic, right?
That's fine.
Because it's uncountably infinite, right? Yeah.
That's like you can squish them. Because you'd have to come in with the total space already defined. This would be challenging to define. Like I'm not thinking it's impossible. It's probably possible. It would be challenging.
Yeah.
Would it be a manifold even? Might not even be a manifold.
What if it was like?
Wait a second.
Like continuously, like it gets smaller.
The example he gave is wrong. Because this total space is definitely, or maybe it is a manifold. I don't know. That does not.
The total space does have to be a manifold, right? Yeah, totally does.
Maybe he's saying, okay, because I'm sure like mathematicians break their rules all the time. So maybe he's saying, oh, let's pretend it's a manifold where manifolds don't have to be Hausdorff and don't have to be paracompact.
But this is pretty sure this is Hausdorff though.
What? This?
Is it Hausdorff? This total space?
Oh, yes, it is Hausdorff. It's just not a manifold.
Why not?
What happens over here?
Oh, right.
But I'm saying if the condition for Hausdorffness gets dropped, then it can be a manifold.
No. But the thing is, I'm pretty sure what this actually is like a set of, it's like a bunch of continuous circles. Like at every point, there's a circle attached to it.
Oh,
wait, does that change anything?
Maybe it does.
Because then it would be like R2.
Then you can imagine it as just
R2. Yeah, exactly.
Here, but
is that how it is?
Here? The line still feels wrong though. Oh my god.
Maybe it's like the line is also like continuously getting larger.
Yeah.
Like maybe it is just like that, and then it's just like that. Like
it'd be like this.
Yeah.
So this is straight. This is curved. I think, is that a 2D event? No, what happens?
No, wait a second. Wait a second. This can't be right.
I think what happened is he just wants to emphasize that bundles can be weird. Like, I guess some mathematicians drop the condition for Hausdorffness on manifolds, which means you can just equip the manifold with like the discrete topology, which means it's a manifold, right? Like even messed up shit like this would still be a manifold with discrete topology.
Yeah, because like there's no way you could take like this and chart it onto any R, right? You can't chart it onto
if it's the discrete topology, yes.
Wait, can you chart this?
I told you.
No, because this point would be different.
Like if you have a torus equipped with a discrete topology, it's always going to be manifold. Or if you have anything equipped with the discrete, yes, topology, it's always going to be a manifold. Because the condition for a manifold is that it has local homeomorphisms, that this is continuous.
Yeah.
But all maps are continuous.
Aha. Okay, but in that case, like there's no way this is a manifold. Like this total space is a manifold, right? Like I can't think of any way that it is.
So I'm saying it's a manifold if it's equipped with the discrete topology.
But then it doesn't look like this.
Yeah, you're right.
So, but then that's just like saying like, oh, I just like take every point and then just go like that, and then I just like equip with the discrete topology, and it's just like boom, that could be a line.
Oh, you're right. Because we're visualizing this crazy shit like this, but if it's equipped with the discrete topology, it becomes like a goop. It literally like stops existing.
Yeah. Wait, so is this like actually?
I was about to say it's almost a 2D manifold. It's so close.
Yeah. Wait, is this? Wait, hold on. So I'm because in the lecture notes, I feel like the guy who made the lecture notes might have like noticed this. So what he's saying is that in this case, the fibre would be defined as S1 if P is less than 0. So remember why P is coming from this real line equipped with standard topology.
Oh, do you know what it could be? Maybe bundles don't have to be made up of manifolds, just topological spaces.
Is that?
Let's take a look.
If that's the case, that's like super cool.
Yeah, I want crazy shit like this, you know?
I feel like that's like, is it true? Because if it's true, that would explain a lot.
It says a bundle of topological manifolds. So that makes me think that, yes, you can talk about a bundle of topological spaces if you wanted to.
Yeah, it has to be topological manifolds, I think, because it says.
Why? It can be topological. I don't see any. Like,
well, in the definition it says where E and M are the definition in the notes at least is that E and M are topological manifolds.
But suppose that it was like if we change the definition, like what if I told you, okay, yes, if you're talking about a manifold bundle, that's right, they have to be manifolds. What about just a bundle, topological bundle?
Right.
I just create a new definition, you know?
Yeah, but I feel like if either that is a thing or it's too crazy for mathematicians to deem it useful.
Well, yeah, I think this is like theory land here. I'm just searching up. Topological bundles are a thing where it's just they only have to be topological spaces, not.
Whoa, okay.
I mean, I guess I don't know. So I guess the example he's giving here is not actually a manifold bundle.
Yeah, which is kind of I'm kind of disappointed by that.
But for intuition, it's great.
It is.
Okay.
What if we didn't do the point? Like, what if we just said like at 0?
Yeah, what would you do? Oh, maybe they're like, not connected.
Wait, but he did say something about this. I'm pretty sure he said something like, what was the point of this? Oh, it was like, wait, did he actually say this isn't a bundle?
I think he was just trying to give an example and didn't think about the possibility that it's not a topological manifold.
Perhaps that might be a thing. I don't know.
Hey,
Well,
you know what we
just,
can
like,
do? We
review
can
it.
ask on Stack Exchange. I asked a question on Math Stack Exchange.
Did you get a response?
Yeah, we should all like boost each other, you know.
Yeah. So that one upvote.
Yeah, I don't know. You know, like why not? This case
Yeah.
too. I don't see. I think this is a good question for Math Stack Exchange. I mean,
Mhm.
what do you think? Let's do a speed run of section. Oh, bundle morphisms. Oof.
Okay, wait, where are we?
About halfway. But
Möbius
thankfully
strip
the
is a
rest
fiber
is
bundle.
more simple. Yeah, we really need to do section. That one's crucial. And then maybe bundle morphisms.
Oh, wait a second. So this is interesting. I just see. So the Möbius strip is a bundle like this. So pi is a fiber bundle like this to this with fiber f is defined as this. But it's not, it is not S1 cross this interval.
Yeah. Exactly. Like the difference between the triplet E pi B, where the first one, let's say this one is a cylinder and this one is a Möbius strip.
Mhm.
The B is the same, right? We agree?
Yeah.
The pi is practically-ish the same. It depends. The pi could be the same if you define both of the total spaces using the quotient space, right?
Mm-hmm.
I don't know. Well, because you know,
Oh.
like when I gave my original example, when I was talking about a cylinder, I said, oh, E is the product of S and R.
Yeah.
But you could also define a cylinder as taking a sheet of paper and gluing it.
Yeah.
In which case the pi would be like the same because you just project down to x0.
Yeah. But like what I'm thinking is
These two are different. This is the difference is the total space between the cylinder and the Möbius strip understood as a bundle.
okay, yeah. I think
Base space
yeah.
is the same, projection is almost the same. The huge difference is going to be this, the total space.
Okay.
Okay, anyways. Good to move on to sections.
Yeah. Actually, well, yeah, actually I think sections are
I think I went and looked at another resource for bundles, and it was a lot more intuitive than the explanation in the video.
okay, yeah, go ahead then.
Okay, here. Section, cross section, that's the intuition. If I have a cylinder like this and I slice off a part of the cylinder, I'm left with a cross section. This is a valid example of a section, right? If I have a cylinder, I have the base space here, and then I give you a cross section here. The choice that I've made visually is equivalent to the choice you make mathematically, right? Because a section is going to be a map that goes from B to E, which basically means for every point of B, make a choice of E at the top here. In this case, I'm saying you make a choice where, you know, it's a cross section that's flat, but you can come up with an angled cross section, right? You can come up with a cross section that looks like this.
Yeah. And basically it's just, so this sigma is just like, so pi after this sigma is just the identity.
That one intuitively you understand. If you take a point of the cross section, you map down, you can map
and then you
back
can
up.
come back, yeah.
Yeah. Or
no.
You start up here, you start down here. You take the cross section and you map back down.
So you start like at the base space.
Yeah.
You do the sigma, which is the cross section, to go to some point on this.
Oh, but keep in mind, this is for every point. What you're thinking of right now would be true for every point. For every
for every point on the base space, you can go to a point in the total space. No, and pi would take you right
cross
back.
Section, right? Oh yeah, I guess part of the total space. Fair point.
Yeah. So basically, the cross section is a map that takes you from a point on the base space to some place in the total space.
Yeah.
Such that if you do pi on this new point, you'll go back to your original.
Yeah.
And pi is the original map from total space to base space, which is how we define the bundle.
Yeah. So practically, it's just like making a cross section in the normal intuitive sense, right? You just take a cross section, except in this case, it acknowledges the fact that the cross section doesn't have to be like a circle, a flat circle. It can be like this, like whatever, as long as.
It can be like crazy.
Okay, cool. Okay.
So it's pretty intuitive.
Cross section explained. Bundle
Are
morphism.
cross section and section the same thing?
Huh? Yeah. I just use cross section because it's more intuitive, but professionally people say like section only. So
okay.
Something to keep in mind. Let's go. Bundle morphism. Okay. I don't know. I feel we can kind of skip over these guys because it's getting kind of like.
Wait, hold on. Subbundle is.
Oh yeah. Sorry, I missed it.
I think it's kind of.
Let's see. Okay. So we understand R2 as a bundle. A bundle between R and R as a fiber, right? Then the sub bundle would be just R. I don't know. I need to find like a practical application of the sub bundle.
I feel like we need like a ton of. I think we need like
examples.
Like a ton of examples. We need practice. I feel like that's what we're missing. Like we don't have practice with.
Totally.
Or like I don't have practice with like topology problems.
I guess in this case, let's just speak of all these terms like high level, blah blah language, and then on our own do like more work here. Let's see, restricted bundle. That one feels like the similar thing where, like if we use our example of a cylinder, you can restrict the bundle to a neighborhood here. Just to like this here, right?
Okay.
Like you just restrict the cylinder to being like just a part here.
Yeah, I think that's what it is.
Yeah, so you'd have to modify E prime as being like the relevant part of E. You'd have to modify
that makes sense. Yeah,
as being relevant, and pi as being like pi the relevant. It's just for each part you take the relevant part.
Mm-hmm.
Bundle morphisms.
Yeah, I'll just do bundle morphisms.
Okay, let's see.
Yeah, you want to just like draw? Yeah,
I'm just gonna draw it. I'm not trying to complicate my life. So bundle morphism is a pair. You actually have to do work and find a map. V. No, V is when you go this direction. No. Oh wait.
No, that's U inverse. So U V. I believe it would be like.
Oh yeah. You're right.
And then this would be pi. Yeah.
Where this commutes, like starting here, ending here, it commutes.
And commutes means like you can go like this, or you can go like this, and you should end up in the same place.
Yes, but I think practically the way you evaluate it is by saying U after pi. No, this is actually pi after U. Sorry.
Pi after U is equal to V after pi prime.
Yes, exactly.
I'm not gonna write here.
Yeah, after V.
But yeah, that's basically what the diagram means, right? Like going.
Yeah. And it's
pi after U is the same as
for bundles.
That's pretty simple.
Everything we've done with classifying topological spaces, like the topological invariance is like classifying them.
Wait, say that again.
So with topological spaces, we've been classifying them into like compact and not compact.
Yeah.
Paracompact and not paracompact. Connected, not connected. And the test that we have is if two topological spaces have different properties, then a homeomorphism does not exist.
But there's no way to check.
Yes, there's no way to. Yeah.
How do you know then?
What do you mean?
How do you know? Because like if you can't check all the invariants, then how do you know that two spaces are topologically isomorphic?
Oh, that one you can do work and prove. It's the opposite. Oh, wait. Yeah, no, you can't know that. That's like kind of an unfortunate thing with topology. There's no finite list of invariants to check.
Because we know that this is topologically isomorphic to this, right?
So well, no, you have to prove that. Like in this case, I would tell you, what if it's equipped with some dumb topology, like both of them?
No, but the topology is what makes it look like this.
Yeah, so what if I tell you, okay, I'm going to equip this with the chaotic topology? Okay, I see.
Because then it wouldn't look like this, right? So
yeah, you've got a point. Okay.
I feel like it's just like, because I remember he said in the beginning of this lecture, This is because he said that this is isomorphic to this topologically because they can be continuously deformed into each other.
Obviously assumed with the standard topology here, because that's how.
Yeah, that's the thing.
But you already mentioned, right? The fact that you drew it's like if the Python function to print out the circle required a topology to already be defined.
Yeah.
Like you can't print out a thing without.
Mm-hmm. So a bundle morphism.
Yeah.
Actually, wait, I just jumped. But yeah.
No, but yeah, I was about to go right to bundle. I think all I was trying to say is that the same story of classifying topological spaces is going to apply again to bundles. We're going to be classifying bundles. I mean, probably not, but it's probably something you could do. And using the properties, you can probably do like instantly know if there is or isn't a bundle morphism between two things. Mm-hmm. So apparently that field is called category theory, like where you start classifying things. Like, you know, this pattern we've constantly encountered, like classifying topological spaces, classifying manifolds, classifying bundles, classifying this class. Apparently that field's called category theory. So I don't know. I'm going to take a look.
All right. Anyway, yeah, bundle morphism.
Yeah, let's.
So bundle morphism is just. So it is when you have like this pair of maps, U and V. But two bundles are isomorphic if there exists a bundle morphism. If there exists two bundle morphisms, one is like UV and U inverse V inverse.
Yeah.
If you can go in both directions, basically, which is actually pretty intuitive.
Sure.
Obviously, right? Because you can go from this bundle to this bundle. No. You can go from this total space to this base space, and you can do the reverse.
Yeah. So that's cool.
Structure preserving, yeah, that's the thing.
Then there is the idea of local bundle isomorphisms. I think, I don't know, that one just has to do with like the Möbius strip is locally trivial or something.
Mm-hmm.
So trivial is clear. That's if it's just a product manifold or not. But then locally trivial is if it locally resembles the product manifold.
Yeah.
Cool. Let's move on. Okay, pullback of a bundle. Okay, it's like when you have.
Yeah, I don't think I understood pullback actually. Just explain real quick, or maybe I
will
did.
Try. So it's like if you have this, if this is the information that you have, so a map from B to B here, then it's like you can pull back the stuff here, and for free, you
create
can
a new total.
A pi prime and an e prime, yeah.
Oh.
Just with this base map over here. I need to do more thinking about this though, because I don't actually have an example, which is unfortunate.
Yeah.
But apparently what happens is if you have a sigma section, you can also pull back the sigma.
Yeah.
Which apparently is extremely relevant in the future, but I have to do more thinking here. I don't have an actual example in my head. So like, okay, let me give example number one. We are going to be talking about the topological space R equipped with the standard topology. What is an example? First of all, we agree this is a topological manifold, correct?
Yeah.
Okay.
It's literally R equipped with standard topology.
Yeah, of course it is. Yeah. And then what are examples of topological manifolds here?
Examples of topological manifolds?
Sorry, of atlases. I'm so
I mean, so if this is R, an atlas is just a collection of charts, right? So like a chart could be like this, and then
no, I'm talking about mathematically here, not hand wavy. Oh yes. Oh. Yeah. That is an example.
Oh, I mean, we could do like a chart could be like -5 to 2.
Yes, that's a chart. What about an atlas?
An atlas would be so like, yeah. So an atlas could be like this. I don't know, to like 2, and then like 1 to infinity. I don't know. Like this is an atlas, right? It's a collection of 2 pools.
Wait a second.
This is a cover.
Just the neighborhood U, but an atlas or a chart is UX, including the map that brings it from U to.
So
but
what
in
if
this
I?
case, just say identity, identity on R. Like that's
Oh yeah, that's true. Or I mean, another valid thing would just be to double everything, right? Like that would totally.
sure. Yeah. Yeah. I don't know.
think that
This
would
is
work.
where, yes. So for continuity reasons, totally. But apparently, like next week, if you pick a choice of a map, like square root of 3 or something, apparently something different happens, which I'm confused about.
Yeah, that's weird. Okay, we have to check that out because I don't know
Yeah,
why
it's
that
about
would be the
3 views.
case.
I don't even know. So yeah, here's a check mark. Well, okay, you actually have to define this. Do you want to rewrite this correct? Like including the identities here?
How do you do that actually?
Well, you were so close, right? It's just a set of charts where a chart is ux. So you had the u parts check marked, but you just need to add the x.
Okay, so I just had like so that would be like, wait, so that would be negative infinity, comma, I don't know, like 2 with
ID, yeah.
ID, and then I would be like itself one tuple.
Exactly.
Or not tuple, but like
Yeah, tuple, yeah, why not?
Structure. Yeah. Yeah, and then the other one too, of course.
Same thing, but
2
yeah.
comma.
Okay. That was
or it doesn't even have to be 2, it could be 1. It could be anything. 2 comma infinity. Because it's like there can be overlap. So 1 comma infinity.
Yeah.
Again with another I. Boom. Boom. That's epic. And that's only 2 charts, and we can make an atlas out of that. This is not it's not a maximal atlas because it doesn't have every possible chart.
Yes, definitely not maximal. Yeah.
Maximal atlas is kind of simple to understand, but it's also like you can't write it out.
Exactly. Complicated to actually get to.
Mm-hmm. And we even talked about like the bird. He kind of like brought that up as well. Like it has to like
with
the birds
C0
in the real world. Huh?
With C0 compatibility. So what you wrote down here, is this C0 compatible?
I think so. Everything's C0 compatible. I shouldn't say everything. Like what does that mean?
Everything's compatible. Yeah.
I mean, it is, but like why?
So what you do is you find the intersection between the U's and the V's. So you intersect, oops, that's an and sign. What's an intersect sign again?
Upside down U.
Oh, that's confusing.
Yeah.
Actually, never mind. It's pretty cool. So in this case, the intersection would be 1, 2. And you need to check if the map from 1, 2, so the map, random letter, 1, 2 to 1, 2, oh shit.
Is continuous.
Yes, it's continuous. Yes. Using
x of 1. So like
reverse cross.
So the chart. So the map from. Yeah. So okay. So the map from this is. So the map from this to. Like this, right? Like the.
Yeah.
The map that goes from this to the real line back to here.
You need to go ID -1.
Yeah. So like the thing from U to R, and then with R being like this thing, and then back to B.
Continuous.
That's very continuous, and the same the other way around.
Why is every Atlas C0 or every Atlas C0 compatible?
Because X and Y are homeomorphisms, so the composition map is also homeomorphic.
Yeah, exactly.
Also homeomorphism.
Exactly.